Super G and
Like the jumping,
jump.
or the like.
Swamp.
The tricks.
Okay.
No tricks.
No tricks.
No.
Downhill, slalom, and GS.
Where'd you grow up?
Minnesota.
Yeah, that'd be the place.
I don't think of that as ski country, but maybe it is.
That's more like barricade country.
Yeah,
literally
little hill with Eric Seiler. He used to be my ski coach, and he taught Lindsey Vaughn.
Those are good
Really?
saves.
That's cool. In Lubbock, we used to go skiing in Angel Fire, New Mexico.
I was thinking like you were gonna say down dirt hills, because that's about all there is there.
The bunny slopes are actually really fun. Yeah. You got the magic carpet, you go up the magic carpet, holds you up, and then you start skiing down the bunny slope. It's great.
I've never been to school. I've been Okinawa a lot.
I've not been
I've
skiing.
been in Okinawa with the city to ski, but I did not ski. That's not.
Why do you ski?
I feel like I would rather
I never broke
do
my ankle.
snowboarding, but I hate the idea of having your
It's
feet
not just gonna
stuck.
snap.
I feel like it
Like,
might snap.
I want the freedom.
Like-
I want freedom.
I was gonna
Some people do that where they like detach the back foot or whatever, but
Yeah.
that also seems a little frightening.
It's weird.
Okay, we got great stuff to talk about today. Very excited. We're gonna have a homework set that will cover this distributed in the recitation. And we want to do a few examples first with our dot product, to make sure we're comfortable with that. And then we want to do a similar exercise to what we did last time with our dot product, or what we'll call our cross product, to work out a few properties of that product. So,
I have a question.
yeah.
When we talked about multiplying and dividing vectors, how would that be asked?
I was just gonna ask that, like, how would
how-
we apply that?
How
Well,
would a person
Have we talked about dividing?
no, not dividing. Well, well, we talked about multiplying by constants, which could include division in some sense. Well, the most straightforward way would just be to literally show you two vectors, A and B. And then to say, what is, have X, Y, Z components literally for both vectors A and B. And then have you say, what is 3A minus 2B, or A dot B, or A cross B, various things like that. Or find the angle between A and B. In fact, let's do that. We'll talk a little bit about dot product applications. And one of the most interesting things we can discuss in the context of dot product applications is finding the angle between two vectors. And in fact, let's just do that literally. Just make up two vectors somewhat randomly. Let's say 3 in the x direction, minus 2 in the y direction, minus 1 in the z direction for our first vector. And then let's say 5 in the x, minus 4 in the y, plus 6 in the z. And the question, in the most straightforward way, could be phrased: find the angle between vector A and vector B. So in order to do this, what we want to do is to leverage the two ways of writing down the dot product. So A dot B, we know, can be computed as magnitude A, magnitude B, times what? Yeah, cosine of the angle between. But we know that it can also literally be computed as AX, BX, plus AY, BY, plus AZ. Easy. So what we're going to do is compute magnitude of A, compute magnitude of B, compute A dot B, literally, and that will leave us with everything numbers except for cos theta. So all we'll have to do then is take the inverse cosine. In fact, to write that somewhat more generally, in a somewhat abstract form, theta between two angles will be cos inverse A dot B divided by magnitude A magnitude. Does that equation make sense to everyone? And if you want to actually compute A dot B, you're typically going to use this one. So you would compute that and put that number in here. And then you would compute magnitude A, compute magnitude B, put those numbers in there, and then take the arc cosine. That would get you where we want to. Now, let's compute our ingredients here. In order to use that expression, obviously we're going to need to know each of these three things. Now, for the magnitudes of the individual vectors, let's remind ourselves that that's the square root of the vector dotted with itself. In other words, it's the generalized Pythagorean theorem. So this would be square root ax squared y squared plus ac squared. Is that good for everybody? Now let's go ahead and get a number for that. And once again, I'm going to suggest to you very strongly that since we know that squaring a real number gives a positive number, let's just not write any minus signs, right? If you really insist on writing your minus signs for AY and for AZ, make sure they're inside of parentheses and you're squaring the parentheses. And if you enter it in a calculator that way, make sure it's inside of parentheses. But what would be the most straightforward and smart thing to do? Just drop the minus sign because you know it's going to square. So let's do 3 squared plus 2 squared plus 1 squared. 100% makes sense to everybody? Any questions? And let's do the same thing for B. So why don't you, I'll write it down, but why don't you write it down without peeking? Make sure you write down the same thing. And then let's go ahead and get a number on this. Let's see, this will be 1 plus 4 is 5 plus 9 is 14, so root 14. And this will be 25 plus 16 is 35, 41 plus 36 is 71, 77. So let's go ahead and get a number on those two things, or we could just leave them written as such. Written as such, they're exact. Unless we put them in a calculator, we've got a constant in most cases. Okay, so root 14.
3.74.
Sounds right. Root 77. 18, 77. All good so far? Okay. Now, let's do A dot B. Now, listen very carefully. I'm going to explain to you the number one way to do this wrong, so that you just won't do it. This is our scalar product. What's another name? Oh, I gave it away. This is our dot product. What's another name for dot product? Scalar product. And what's the word that we use geometrically? Parallel. Okay. So scalar product. Scalar, not a vector. Do you see any hats over here? There are no hats, right? All the hats went away. We saw what happened to them. The x hat dot x hat turned into 1. The x hat dot y hat turned into 0, and so on. All the hats went away. The number one thing to do wrong here is to try to put hats back into this thing. Don't do that. This is just a number. This is just a number. This is just a number. And then you're just going to literally add them all together. There should be one number at the end if you're working with numbers. So A dot B should be, I'll put them in parentheses here just to indicate multiplication and to group our minus signs. Should be 3 times 5 plus -2 times -4. Minus signs are definitely important here. They need to come along. And then plus -1 times 6. Just AX, BX, AY, BY, AZ, BZ. Add them up. They're just 3 numbers. They should be added together. So 3 times 5 is 15. 2 times 4 plus 8. -1 times 6 minus 6. So all together, what have we got there? 17. Looks right. So now, what we're going to do is put all the pieces together. Theta should be arc cos A dot B over magnitude A, magnitude 3.74, 8.77. So on a calculator, let's say 17 divided by 3.74 divided by 8.77. Everything on the bottom gets its own divided by. Enter cosine inverse answer.
Use the exact numbers.
Sure.
58.78.
Everyone agrees?
8.82.
We'll get some rounding error.
That's the problem from the other side.
So that's that. I'll show you one more real quick application here. It's basically it's a neat thing that if you didn't know this trick would be wildly difficult to figure out. Wild and difficult. So if you had a square and you drew a line from one angle to the other, obviously, you know immediately that was 45-degree angle. But if you had So if you had a cube like that, okay, and imagine, for example, that you drew a line from one side of the cube to the farthest diagonal of the cube. Which way you'd like to do it? Here to here, let's say, or from here to here, whichever way you'd like to do it. And let's say you want to find that angle between those two things. So if you didn't know our wonderful little trick, how might you go about that? Well,
Cut them into separate triangles and then
yeah,
basically find out that angle which way.
maybe. I'll scratch your head for a little while. I try to get some paper and protractor out.
If you think about them as 2D objects, just do what we have already.
If you can figure out how to
We're assuming this is-
appropriately slice that and find the size of the triangle, then that might work, yeah. Take a look.
We're assuming this is a perfect cube, right?
Yeah, perfect cube. Yeah, so each of the sides, say, call it A, let's say. Is it obvious that I don't have to tell you what A is? Just stretching the cube would not change that angle. So when we're done, that A, it better cancel. Okay. So what I'm going to suggest we do is, let's call this the 0 point of our coordinate system. And we're going to label our 3 axes, and just to be consistent for future purposes, we're going to choose what's called a right-handed coordinate system. We'll have more to say about this later today. But a right-handed coordinate system, it means you can't just call anything x, y, and z that you like. Once you've defined x and y, you know there were 2 choices for z that are perpendicular to that, right? But we always agree to choose the same combination. So right-handed coordinate system goes like this. So first thing is make sure you're using your right hand. It's very important. And start on your thumb and work your way around. Thumb, forefinger, middle finger, x, y, z. So let's apply that to our diagram here. Let's see. I'm going to do x. Y and z. How about that? Good. So let's call these 2 vectors names. Let's call that one A. Let's call that one. We have to call them names. Compute them. It's required. Okay, so what I'd like for you to do is to write an explicit expression for each of those 2 vectors in terms of their x, y, z components and the unit vectors x, y, and z. You will write it explicitly. So write A equals and B equals. They each have an x and a y and a z component. So just read their x, y, z components off of the diagram and then put them in front of x hat, y hat, z hat. Okay, what did you get for vector A? What's its x component?
Yeah, that's.
Well, a sub x. I guess you could write. That's true, but that's not exactly what we want.
That little one.
Oh, you meant little a. Okay, good. That's my point. So it's x component, ax is little a, good. In the x direction, what was its y component? Little a. And what was its z component? Perfect. Is that what everyone got more or less? Or at least we see, yeah, kind of close. Do you see that that's right?
Yeah, I see it.
And vector B.
I just got A. Just A.
Yeah, you see what
AX hat.
That's right. Okay, good. So its y and z components are 0. Is that clear? Yes. Okay. So what I would like for you to do now is to find the angle between them.
Interesting.
These are the 3 ingredients that you should need. Calculate each of those 3 ingredients. They'll all be in terms of little a, that's fine. A dot B, what did you get?
A squared. Plus A plus A. I got just A squared.
So there's, yeah. It's going to be A times A plus A times what?
0.
0 plus A times 0. What's the length of the A vector?
A cubed.
No.
Square root A squared plus B squared.
We can simplify that. So square root A squared plus A squared plus A squared. What do you simplify that to?
Or 3A. But 3A squared.
3A squared under the radical.
You can,
Then let's simplify just a little further.
A square roots of 3.
Good. And what's the length of B?
A. Just A.
If you like, you can write that as square root of A squared plus 0 plus 0. Okay, so theta let's write arc cos. What goes in the numerator?
A.
It would be A squared.
A squared, right?
That's right. Yeah. A dot B in the numerator. And I mean, don't memorize this. Memorize the 2 versions of the dot product and then write this down. Or better yet, understand the 2 versions of the dot product. Divided by
A squared root 3.
Uh-huh. It's
yeah, and then times.
Works out very well then.
Yeah, right. That's what happens to our A's.
They cancel.
Yeah, of course they do. Because our answer physically could not depend on A. So that. Cosinverse 1/√3. Something like 45 degrees.
Something.
54.74.
It looks so pretty.
Can everybody do that? So let's talk about our cross product for a little while now. We're going to call this our vector product. And once again, what that means is that we're going to take vectors on the input, vector times vector, and we're going to expect to get a vector on the output. We do have to be careful, of course, that we define this in such a way that what we get out really is a vector. And what that means is it's got to rotate along with, alongside the original two vectors. So we're going to give this a special notation. We're going to give it a special name. The name is cross, used interchangeably with vector product. And the special symbol is a cross. And we want to think about what reasonable definitions could be. And then the constraint of what reasonable definitions could be, we want to find something useful. And of course, what we're going to suggest and motivate at the end of the day is the conventional definition of the cross product, which satisfies both of those requirements. Since what we're getting is a vector, the first thing we need to recognize is that being a vector means two things. You have a what and a what?
Magnitude and direction.
That's right. So, in essence, for the dot product, the scalar product, we had to define one thing. What's the magnitude? For the vector product, the cross product, we're going to have to define two things. And let's think about them separately, what reasonable choices might be to consistently define this product. Now, the magnitude itself, the magnitude of a vector is itself what type of object? A number. In other words, it's a it's a length. It's a scalar. It's the magnitude of the vector. The length of the vector, the magnitude of the vector is fundamentally unchanged under rotations, right? That's the true definition of a scalar.
Say it one more time.
The length of a vector is fundamentally unchanged under rotations. That's the most basic definition of a scalar, something that doesn't change when you rotate. So the magnitude of the vector itself is a scalar. So we're going to have to come up with two definitions. A suitable definition for what the magnitude of the cross product is, and a suitable definition for what the direction of the cross product is. Now, let's use our intuition that we developed last time. If we want to build a scalar, we need to build it out of things that don't change when you rotate. So what do we have at our disposal? Well, we have the length of A. We have the length of B. And it stands to reason, since this is a product, they really should come in each once. Linear in both things that we're multiplying. But the other thing that we have, which does not change when we rotate, given that we're rotating these two things what? Together, is the angle between them. But angles don't normally run around by themselves. Angles are best behaved when folded up inside of trig functions. Trig functions. So natural choices for this definition would be sine or cosine. In fact, if we pick cosine in this particular case, we'll run into an inconsistency, which I'll point out to you. Sine is the choice that really matches the flavor of the product that we're trying to assemble here. That's all clarified hopefully in a few minutes. Let's think about a drawing. If I had two vectors A and B, just like we did last time, this is the angle between them. I can draw a perpendicular bisector, and I can define these two lengths here. This length is A times what trig factor? And this opposite side, this side. So for the dot product, what did we end up choosing? Cosine. That's right, parallel was the intuition there. And it also matched our physical intuition of things like forces times distances. Force dot distances work. The force and the distance need to be parallel to each other. If instead we pick the sine, what's the geometric word that ought to go with this product? Perpendicular.
So for the other one, are we to assume that the angle really didn't have as big a factor as this one does?
I don't understand.
Maybe I'm overthinking it. Never mind, just go ahead and I'll call
The angle is very important to both. Okay. The magnitude of A cross B is all of B times the part of A that's perpendicular to B. Or, we should say both ways, all of A times the part of B that's perpendicular to A, which you can see. The critical intuition, these three words, forever melded together in your mind: vector product, cross product, symbol, cross, and perpendicular. In fact, the name and the symbol are very well chosen for the intuition we're starting to build up. Perpendicular part, doesn't that look like an X? We're taking the across part. That's going to come to bear you in one additional way as we start to think about the direction. What I want you to think about, just brainstorm for a minute. We're in a three-dimensional space, X, Y, and Z. I've given you two vectors, A and B, right? What I want you to think about is, if I'm going to assign those two vectors, product, to be in some third direction, I need to make a definition of what that third direction could be that would be uniquely recoverable from those two vectors. Does that make sense? So I have two vectors there, A and B, and by the definition of saying that we're searching for a vector product, the product relative to A and B ought to be some third direction. We need a unique definition for what that third direction could be. Okay, so you said kind of between them. I think that's not a crazy suggestion. So you would have to, it would rotate with them in some sense. That's fair in some sense. You might have to sort of weight it a little bit based on which one was the longer one or something like that. That's not the way we're going to go. Is there a direction that these two vectors uniquely define? Yeah. The direction that has what relationship to them? There's our word again, isn't it? The direction that's across from both of them. So the direction we're going to define is the direction that's perpendicular to both A and B. In other words, what? Any two vectors define a what?
Plane?
A plane. And we're going to define our result to be perpendicular to the plane. Do you find any loopholes in the statement I just made? What was the statement? Any two vectors define a plane. Are there any loopholes in that statement? Put them tail to tail, and some angle between them. So I have two vectors. Two vectors. These two vectors, they define a plane. Are there any loopholes in that statement? Well, the statement I made was any two vectors always define a plane. Any loopholes?
Maybe if one of the vectors is 0.
Okay, good. That's a great loophole. If one of the vectors was 0, they would no longer define a plane. That's good. Okay, if they're 180, do they define a plane anymore? I can.
Not really. More line.
Okay, good. Now, when they were like this, they defined a unique plane, right? The plane that touched both of them. If they're 180 or 0, if they're either 180 or 0, then they don't define a plane anymore, right? It could be this plane or that plane, or, ooh, I don't know which plane I mean, right? Ooh, okay, so there's a loophole. There's a loophole. Our direction is not well defined. In fact, you guys found all the loopholes. That's great. Yes. Listen, good physicists and good computer programmers have to do better than lawyers at finding loopholes.
Yes.
And we have a big advantage. It's just the system we're working with actually makes sense.
My government teacher used to tell me that everybody should get a law degree first and
Yeah.
then pursue the degree that they want.
Interesting. Okay. Our perpendicular direction is not well defined if either length is 0 or theta is 0 or what? Is that a problem? Say, oh, our definition doesn't make sense anymore if either of these things happen. Guess what? We're beautifully protected. Can you figure out how we're protected?
Because at those 2 degrees, sine is 0.
That's right. Well, and equivalently, if A is 0 or B is 0. These are precisely the circumstances these are precisely the cases in which A cross B is equal to 0. So, no direction is needed. Oh, goodness. So, if we had chosen cosine, our definition would have been fundamentally flawed, would have been inconsistent. We have to be careful that we make a definition that's consistent. So, do you see how beautiful that is? Just at precisely the moment that we lose the ability to define a direction, we don't need a direction. Perfect.
It's almost like it was made that way.
Now, there's one other problem I haven't mentioned. Is my direction uniquely defined?
Should. Is your direction?
Okay, so I've got two vectors. I've got two vectors, A and B. Our favorite two vectors, A and B. And the statement was that the result of their cross product should be perpendicular to both of them. In other words, perpendicular to the plane that connects them, right?
So yes, it is unique.
Is it unique?
Yes.
Okay, get your lawyer hats back on. What's the problem? So I have these two vectors, right? I'm going to hold them fixed. would you each please point in the direction perpendicular to these two vectors?
Perpendicular. Oh. 'cause
Oh.
It could go either way.
There's two choices? Ah. So, it looks like if we define the direction perpendicular to A and B,
Be negative or positive.
that's right. We have a twofold ambiguity. A twofold ambiguity. What'd you say? Just choose one? In some sense, but we've got to be sure that we all always choose the same one. So we have to make a rule. We have to agree to it. We have to be absolutely firm that this rule is always. So I want to suggest to you that this situation is precisely like the difference between your
Left and right.
left hand and right. So if this is one vector, okay, I'm doing everything the same, right? I've got my first vector. I've got my second vector. Go Raiders. All right, these are both the same, right? My third vector could either be this or this. We are going to agree. In fact, I'm sorry to say we agreed before you showed up. Before I showed up, everyone agreed before we got here, I have to report to you, that we will always do it this way. In other words, we will always use our right hand. Now there's one other thing you should have noticed. Did you hear me use the words first and second? First vector, second vector, result. The cross product matters what order you do it in. A cross B is not the same as B cross A.
It's a different direction.
It's a different direction. Can you tell me what the difference is between A cross B and B cross A?
One's the straightforward direction, the other one's.
They're precisely the negative of each other. So, what we're going to define in order to solve that twofold ambiguity is what we call the right-hand rule. What's the most important thing about the right-hand rule?
Right hand.
Use your right hand. Guess how many people start working on their test and they say, oh, I'm writing with my right hand. I'm going to do this thing with my left hand. Good idea? Bad idea. Right-hand rule. There are a couple different ways it can be done. And in fact, what we start studying electrodynamics, which is really a place that the right-hand rule pops up all over the place. You'll see a few different things that are called right-hand rule, but they're all at the core basically the same thing. Remember a second ago when I said we're going to go around like this? That's basically the same rule. Isn't that what I just told you? First vector, second vector, result. Or you can go first vector, second vector, result. Same thing, right? We're just working our way around like that. In fact, the way that I usually like to do it is to say, the first vector corresponds to your forefinger. So line your forefinger up with the first vector. Second vector corresponds with your palm shooters. This can be your Iron Man repulsors. This can be your Spidey webs, whatever you like. Forefinger, first vector, second vector, and the result is your thumb. Now, what we're going to see next time What we're gonna see next time is that we're gonna write this cross product out with vector A and vector B explicitly, like we did before. Vector A has how many components in general? 3. Vector B has how many components in 3? So if we take a product of 3 and 3, how many terms should we get? Same 9 terms we had last time? Except instead of dots, they are now crosses. Last time, how many of our 9 terms survived? 3. And how many disappeared? 6, because 6 of them were not parallel. This time, how many are going to survive? 6. Because now we're keeping the terms not that are parallel, but that are perpendicular. And guess how it's going to work? X direction cross Y direction, which way is that going to point?
Same way.
Well, what's perpendicular to X and Y? Z. And we're going to follow the cyclic rule. X cross Y is Z. What's Y cross X? Negative Z. And the way you can tell is that it's out of order. Y comes after X, right? What comes after Y? What comes after Z? X. Okay. So if it's in order, it gets a plus. If it's out of order, it gets a minus. And we're going to find that there's 6 terms which combine together into the X part, the Y part, and the Z part of the result. So we'll write that down explicitly on. Okay, see that.
I'm assuming you're gonna leave the direction part of the equation on Friday as well?
Well, that is the right-hand rule. That's what I didn't write something explicitly, or we described it in words, so that's what that is.
Are you in our group chat by chance? Okay. Just want to make sure. You don't really like respond much, so I want to make sure if you needed help or anything, or vice versa, you should have access to it. No, it's all good. Just like didn't want to leave you out because I felt like you might have been the only one that we didn't. What's your name, by the way? Daniel? Steven. Nice to meet you officially. I don't think you do.